Can you hear me? Alright, so this is 10 p.m. in Japan time on Sunday. Let me start the live stream of Houdini for this week. Hello, this is Junichiro Horikawa, and this is a tutorial live stream for Houdini. And today I am going to try to use this new feature from Houdini 20.5 called Copernicus. And specifically, I'm going to try to use the OpenCL node to get started with the feedback loop features or functions. As an example, I made a small example using a feedback loop technique to mix the color through time using just a simple OpenCL node with some small script, and which seems to work pretty well, and it runs pretty smoothly real time. So that's what I would like to show you today. And yeah, I think it's going to be the setup itself is pretty simple, and once you know the rules, I think you can use it for more advanced purposes. The Copernicus itself, I think, really looks pretty awesome. I mean, I haven't really tried that much yet, so I don't know much about it yet, but I'm still learning. But at least I wanted to know if I could do this feedback loop things like these color mixing stuff and so. And yeah, it seems it's possible. So I wanted to show, I wanted to share that with you guys for today. Okay. So in terms of Copernicus, seems like it doesn't work pretty well in Mac OS's OpenCL shaders. So if you want to use old Copernicus for now, you probably might want to use Windows with Vulkan shader. Okay, so let's get started. I have connecting to my Windows PC from my Mac right now, and let's see how we could do this. Now, before getting into the detail, I can share some of the resource how I learned the Copernicus as getting started. First thing first is one of the basic tutorial on Houdini side effects website showing us how to get started with the Copernicus, mostly using Node. I just watched the first one, but it was really good. It was really great. I think if you just started learning Copernicus, I think this is the video to go for sure. Yeah, this was really great. Now next, there is a page on a side effects document page where it says OpenCL for Vex users, where if you're new to an OpenCL, it shows a bunch of necessary informations you need to know when you're writing a OpenCL code, especially if you know Vex, how to write Vexes. And yeah, this is also really important. And in our case, what we need to look at is, first of all, these global bindings, where you can access a bunch of global attributes like the number of X index, the number of Y index, and so on, as well as some functions for the field. And there are several functions available in many contexts. For Copernicus, there is a specific a context, which is for this one, layer binding method. These are the one we can use inside OpenCL node for Copernicus. So we have to get we gonna check these out later. Now there's other site I found really helpful, which is this one. This is not sure what's the name of the website. It says Houdini tips and tricks, vfxmentor.com, and it has a new page for OpenCL, for Copernicus, how we can use Copernicus as a basic, and it has a lot of useful informations as a text, and I think it's really useful. And it also has several like OpenCL snippets. We can just grab it and test, which is pretty cool. So this is another great resource. And finally, the OpenCL grammar itself. There are some, OpenCL is pretty bare-born. It doesn't have much function itself. So we have such as like Perlin noise and stuff. So we need to know what kind of functions we can use on OpenCL, looking at this basic documents, such as like, I don't know, F, abs, something like that. This is the last page to go when you are stuck with coding. Okay, so let's get the other one. I'll show you the other resource later. There are another one which is pretty useful as well. Okay, so to get started with the Copernicus, I'm going to start by creating a geometry node. First thing first. Then create a COP network. The old COP network is the previous versions from until Houdini 20, and this new COP network is the Copernicus, which is still in, seems to be still in beta mode version. So it does crashes a lot, even in Windows using RTX 4090. So I think you're gonna see a lot of crashing window, but bear with it. Let's get into the COP network and let's get started. Well, first thing first, I'm going to start with some constant value, which is just a single color where you can choose the color by yourself. How was it? Okay. So in this case, I'm choosing grayscale. Not sure why. Not sure how I can change this to a RGB color. Forgot. Think there was, oh yeah, if I change this to signature to RGB, you can now change it to some colors. Okay, let's set it to yellow for now. Now the purpose of this live stream is to get started with the OpenCL and the feedback loop, and the reason why is because I wanted to like create some sorts of solver like simulations within a Copernicus. That's what I wanted to do, just like you do like shader coding. Yeah, so I wanted to know if I could do that, and seems it's possible, so I'll show you how I did it. Okay, so let's bring up OpenCL and let's try to write down code one by one to see how this works. Okay, so when you open this up, you have an input called source and output called DST, which can be defined here, right here. So the input has a source named as source, and the type is varied, could be any type, and it's also optional. For the destinations, it's also varied, and which you only have one stuff. Now, in order to make a feedback loop, you need to have both input and output the same name, source and destinations, to pass the data to the next layer, to the next buffer, I think. So first thing I will do is to create source and destination, and let's not make it optional, on both input and output. And since I would like to use these input as colors, I'm just going to fix the type to RGB, which is a float 3 type in OpenCL. So, well, which you don't really need to, but it's I think it's easier to do with RGB with float 3. So we have source and destinations on input and source and destinations output sharing the same name. Okay, so that's the first step that I would like to do. Now let's also save this because I know it's going to crash at some point. Okay. Now going back to the kernel, you have to register these values to the kernel code. So what you need to do, this AND mark indicates that you are going to have both input and you're going to have an output. And if you have a apostrophe mark, this means you don't have an input, but if you remove it, you're going to have an input as well. Okay, so make the destination looks like this, and we have also defined the type of the input and output, which is float 3, so I'm gonna write it as float 3 on the last. Now for the source, the question mark means it's optional, but it's no longer optional, so I'm gonna remove it. It's also input and an output, so create AND to the source, and this is also a float 3. Okay, let's see if we still got any errors. And yeah, we do. And it says DST is missing, so maybe I think I need to fix something here. Okay, let me check. Okay, so we have to input something to the destination DST input right here, because this is not optional anymore. So you have to connect this. Yeah. Now, now this works. Now to get, well, this is just the input setup. The next thing I would like to do as a setup is to make this loopable. Feedback loopable. And you can do that by going into the option tab and check the use write back kernel. Okay, so this kernel will give you the ability to write back the destination texture back to a source so that you can use it back again in the next frame. You can use the updated texture for the next source frame, source texture in the next frame. Okay, so the reason why I'm getting this error is because I have to have the kernel code written in the kernel tab for the write back kernel. So let's create that one. Going back to the kernel, what we need to write is at write back source dot set dst. This indicates that we are writing back this updated destination texture to a source in the end. And now we have no errors anymore. Okay, so this is the basic setup for the feedback loop. And the reason why I know this is because I saw it on the help of this OpenCL Copernicus node menu, where there is one example which is pretty useful in the last, this one, a game of life. So if you load it, this actually is a example of a feedback loop solver like simulation. And once you load it, what you can see is these game of life simulations, which is using OpenCL to simulate. And this is where I learned how to set up for the feedback loop. Okay, so we have a bunch of codes. We have these inputs and outputs, set it as an unmark signature. Both will have source and destinations. In the option we have use write back kernel, and also setting a frame values on the iterations. And then we have these write back kernel. So if you are if you want to use the feedback loop setup, I think you can just import these samples and reuse it for your purpose. Okay, so let's get back to where we were. I'm going to delete this one. Okay, so let's try using this feedback loop to update the pixels of this texture in some way, in a pretty simple way. So to make it obvious to see the pixel moving, we need to have something other than constant, I think. So let's create something. We could maybe, let's see what we have here. We have, I don't know, maybe we can use another OpenCL to update pixels as a practice. Okay, let's start with the white color, use an OpenCL, another OpenCL, which in this case I'm not going to change any inputs and outputs. Just gonna input this one here. Let's say I want to make the pixels based on the UV. So if the X direction is U and Y direction is V, I might want to colorize these each pixels based on the UV value. So it could be this point could be 0, 0. This right top corner could be 1, 1. So let's see how we could do that. And that's where we can kind of know the basics of OpenCL used in Copernicus or in any context, I guess. Okay, so first of all, let's go back to the document where we have a bunch of global variables right here. Where it says ix. Oops. Just removed it. Okay, now what I would like to do is to, based on some informations we have right here, we could either use something like the x coordinate and y index, x index and y index of the texture, together with the resolutions to update the color, or we could also use add p and so on. So in this case, let me use these values. So what I would like to create for each pixels is to have a normalized value from 0 to 1 based on where the pixels are, from left down corner to the top right corner. Okay, so let's bring those variables up first of all. In order to bring those values to be able to use inside OpenCL, seems like we have to write something like this. So let's bring up ix, iy, or it could also be ixy, which is a float integer 2 value. So let's bring this up. Okay, so in order to bring this up, it's OpenCL is pretty strict with the types. So if you miss the types, it's gonna give you a really severe error. Sometimes it crashes, so be careful. I'm gonna name it as p-index and bring up the global variable value like this. Oops. Now doesn't seem to. Okay, I think I don't need I. Wait. Oh, it's ixy. Okay. Now, what you need to do is to first determine the variable type, which is integer 2 in this case. Name the variable, and bring up the value that you want to use as from a global variable, and cast it to a specific type. In this case, I might not need to cast it. Let's see. Yeah, because it's already is an integer 2. Okay. Now, in order to normalize it, you need to have this indicates the pixel number for x. It's starting from 0 to 1, 2, 3, 4, 5, 6, 10 to until the end of the pixel, like could be 1000 or something like that. So what we need to have in order to make it normalized, meaning to rearrange the value from 0 to 1, we need to have the end pixel value, which is this resolution value. So we can get this at res, which is also an integer 2. So let's get that. Integer 2 res is equal to at res. Okay. Now now we have two integer value, and what we want to do is to divide the x coordinate of p index with x coordinate of resolutions, y coordinate divided by y coordinate of res. And in OpenCL, we could divide two vectors together to make each component, each coordinate divided simultaneously. So let's try to do that. And as a result, we need to have a float. So let's call this float uv and try to divide in p index and resolutions. Now there's a problem with this one because these are two integer 2, so I don't think you can divide it to make it as float 2. It gives you this kind of severe errors. So what we need to do is to convert these two to a float 2 value. Okay, somehow. Now let's see if I could convert it directly from integer 2 to float 2 for both of them. Nope. I think you need to separate the x coordinate and y coordinate independently and remake it as float 2. So let's do that. What I'm going to do is to for the float 2, I'm going to give the index x and y, res x and res y, and probably I also need to cast this to a float. Oh, worked. Okay, maybe not. So hopefully this worked. Let's try to use this UV to directly color these as a RGB value. So what we need to do here, in order to update the destinations, I mean, this is right now, it could be varied, it could be either RGB or UV. So I think you could directly set this UV to this destination in the last line. So let's replace this source UV and see what happens. Okay, maybe not. Okay, and now passing arguments are here index layer. Okay, so I got some errors here, so let me try updating this UV to float 3 or float 4 to make it as color value. Probably I might need to make it as float 4 because of the error I saw here. It says float 4. So if I don't specify the value, maybe I might need to make it as float 4. So in that case, it means RGB and alpha. So if we're having alpha, then let's create a variable called col as a float 4 and cast it as float 4, and inside the parenthesis you enter 4 numbers, 4 values. One is UVX, UVY, and for the blue value it's going to let's make it 0, and for the alpha let's make it 1. And you also, if it's float, you also need to have this f in the end of the value, and you cannot say 0f, which is possible in other programming context, but in OpenCL it's pretty strict. You'll if it's float, you always need a dot and some numbers afterwards. Okay, so even if it's just 0, 1, you still need 0.0 here plus f if it's float. Okay, now give that to destination. Okay, so this is UV. So let's try to use this UV color as a starting point to test the solver, shall we? So I'm going to reconnect this to the second OpenCL one, where we want to create the feedback loop. Okay, let's look at this from the front side, and let me first give a things that I want to try to do here. Now what I want to do is for each pixels I want to, for starter, I want to try to move this one step to the right side or left side. So if this was green in previous frames, I want to make next frame, I want to make this pixels green in the next frame, and keep moving these pixels to go right. Okay, and in the seems like this Copernicus has its endless tiling in the backends, so even if it goes outside the boundary, it goes back to the starting point from the left. If you go outside to the top, it goes back from the bottom. Okay. So what I want to do is to shift the pixels to X coordinate for a starter using this feedback loop. And if we could do that, then we could use it for more advanced features like color mixing and stuff. Yeah. So let's try that, shall we? Okay, don't forget to save this every time you made a changes because it crashes really well. I'll tell you that. Okay. Okay, so in order to move the pixels right hand side to the right hand side, you update the current pixels with the ones on the left hand side. You need to have information from the previous frame. And in this case, the previous frame texture is the source, and this destination is the next frame texture. So what you need to do in this kernel, you don't need to do anything in the write back. What you need to do in this kernel is to refer to the source, refer to where you are right now, using UV that we have just tried. Let me draw this again. So let's say if we are right here in terms of IX and IY, which you can convert it into some kind of UV value. Okay. What you want to do is to refer to the color from the previous textures at this point, at this positions, and which you want to read from source. Okay, get that color and paste it back to this position to a destination texture. Then you'll be able to move these pixels to the next pixels in the next frame. And if you keep doing that for every pixels, it seems like it's shifting the pixels from left to right. So that's what I would like to do. And let's try that. Okay. So to do that, you need to have the current UV like you did here. So let's have that first. And let's copy this up right until here, I guess. And paste it here. I don't really need these one. Now this UV. Actually, you kind of need to add 0.5 to this if you are really want to get the precise UV value. Don't forget to add F. The reason is, well, this is, I think you need to know this. So the reason is because if you have an image like this and have divisions like these, each one has its index for X and Y. So this is 0, 0, 0, 1, no, sorry. This is actually 1, 0, 2, 0, and so on. This is 1, 0, 1, 0, 2, and so on. And this is like 1, 0, 0. This is like 6 and 6. Okay. Now, and if the number of pixels in the X and Y in this case is And 1, 2, 3, 4, 5, 6, 7, right? So if you just divide the p index x by resolution x, for example, if it's 0 and 7, the result is 0, right? If the end, if it's divided by, if it's 6 and 7, if it's 7 divided by 6. And this value indicates the position from here to here, okay? Which is not ideal because as a pixel positions, what we want to have is somewhere around here in the middle of each cell, okay? So to get the middle position, it's ideal to have additional 0.5 to each index, so that as a result of this calculations, p index divided by res, you get these center positions of each cell. Okay, so that's the reason why we have this 0.5. Okay, so that's just some tips. I'm just sharing the things that I learned throughout the things that I get confused. Maybe you already know this kind of stuff, but I thought it's pretty essential and important, so I wanted to share it. Okay, now that we have a UV, let's try to use this UV to sample the texture from source, which is this one, the previous frame textures, and update it. Use that color to update the next frame. Now if you don't change the UV at all, then it's just going to give you the same color, but I want to check if that's possible for a starter. Okay, so in order to sample the color using UV from texture, you need to look for some functions to do that. In Vex, you can use something like UV samples and stuff like that, but there are no functions like that in OpenCL. But what you need to use is, first of all, go to the layer binding method under OpenCL for Vex page, and if there are a bunch of sampling functions in different contexts, different spaces. One is to the one that says sample here is the one you can use some kind of coordinates to sample the color. It's pretty interesting. You have a world to image, so you have a world space, an image space, a texture space, and a buffer space. Okay. Now the explanation of these spaces could be checked under this page. I think yeah, in the first second paragraph of this page, it shows the different spaces. What's the meaning of different spaces for the Copernicus, which is pretty useful. Now for our case, in this example, we're going to use a texture space, which is from 0 to 1 as a range. So let's see how we can sample the textures. And there is one function for OpenCL where we can use UV value to sample a specific texture, which is this one, to get the specific color on that texture. We're going to use this one. In this case, we are going to say at source.texture sample UV. You'll be able to get this color of this texture on a specific UV. So let's try that. So in our case, the source is float 3. So the result what we're going to get is flow 3. Let's call this color. And we're going to sample from source and sample texture UV. Okay. Oops. Okay, let's see what's the error is. Source sample texture unknown method. Maybe I misspelled it. Texture sample, okay, sorry. Texture sample. Okay, now I haven't used the color yet, but if I replace the source with color, I'm simply going to get the same result because I'm just getting the same positions color. Okay, so no changes at all. But now, if you want to shift this, if you want to get the one that's next to it, you could do that by subtracting the UV's U value if you want to move the X value. So let's try that by saying UV.X. So what we want to do is to refer to the one that's left to it, which is the negative direction from the current. So subtract the current X of the UV by some small value like 0.1. Maybe that's not that small, 0.101. Okay, and now you see that it's a bit shifted to the right. The pixel has shifted to the right a little bit. Now it doesn't really animate at all at this point, but you see that it is sampling from the right hand side. So for this pixels, if we are to samples on the left hand side, there are no ones on outside the boundary, so we're going back from the right edge. We're getting the sample color from this part. Okay, so the next step is to make it iterable through these frames. So we want to continue doing this throughout the time. And now that's easy. We already have the kernel back. Right back kernel. We just need to go to the options and set these iterations to the current frame. Now if we play it, we can now update each pixels using the rule that we have just wrote. Okay, same for the V value. We can say uv.y minus, or this could also be plus, which goes to the opposite direction. Okay, so this is already a basic feedback loop. And having this set up, you can just make any kinds of solver-like simulations just inside OpenCL. Okay, it's pretty nice. So the next things I would like to try is to update these code a little bit more to make color mixture simulations throughout the time. Okay, and you can see that it's pretty decently fast. Now I found out that there's another way to make a feedback loop by looking at this page from Houdini tips and tricks. On the page where it says creating a feedback loop solver, it says you could also use a block node on Houdini, Copernicus network, together with the invoke node, and use these together to create a feedback loop as well, which I found was pretty useful because you could connect different types of Copernicus node other than OpenCL. So I thought it's pretty useful, and I tried it, and it did work. The downside is that it's a bit slower compared to just writing in OpenCL. That is because this is pretty similar to what we are using feedback loop in Houdini SOP context. So it's not really a solver, but it's more like a updating the feedback loop for each frames. For each frame, you are recalculating every iterations for each frame. So it's not really actually getting a value from the previous frame, but it's actually re-instantiating or reinitializing the calculations for each frame. So later you go, it's gonna get really heavy in the end. So I did compare using this method and just the OpenCL method, and both works, but this method takes a lot of time to calculate in the end. So, well, if you're interested, you could also go to this page and download the samples for testing. But either way, this is pretty powerful as well, I think, because you could, I mean, in this case, you don't really need to have an OpenCL to do the feedback loop. So if the timeline is not that like long, you could still use this, and it's pretty fast compared to just using Vex, I think. Okay, let me check the comment. So are texture coordinates in OpenCL the opposite of those in DirectX? I am sorry, but I don't really know. I don't really know about the DirectX. I don't even do shadings myself much. What are advantages of using OpenCL versus using Vex in geometry context for 3D context outside of Copernicus? Well, one thing I can say is that it could multi-thread it, and it's pretty much faster than Vex, even though it's pretty tricky to use because it gives you a bunch of errors with small mistakes, which could be passed with the Vex. So if you found probably Copernicus, I mean OpenCL is good for a heavy simulation purposes where Vex is not enough in terms of the performance. Maybe OpenCL works well if you have a bunch of simultaneous things to calculate together. Otherwise, I think using Vex is good to go. But for Copernicus, you can't use Vex, I think, so you do need to use OpenCL. So I think in the page where it explains Copernicus on side effects, it also prefers you to start learning OpenCL as well. So yeah, I'm gonna start learning this. Okay. Yeah, I think George is answering the things that what I wanted to say. Okay, thank you. Okay, so let's get back to where we are right now and try to update this code to mix the color, shall we? So to mix the color, what I would like to do is so right now the moving direction is constant. I'm just subtracting or adding constant value to specific directions. So you could define this as moving directions, right? So what if we could make the directions more randomish, more noisy, so that each pixel will refer to different pixels? And also not just replacing the color, but try to mix the color by adding two colors together divided by 2 might gives you some different result. So that's what I would like to try out. first of all, change the direction using some noise function or noise related stuff, and also try to mix the color from the previous one and the current one. Okay, so let's do that. And in order to do that, we need to access some noise functions. Now, the OpenCL itself does not have a noise function. It was also mentioned in this page as well. Now it says there is a pre-made functions where a Houdini side effects has prepared, where you can import it and create a polling noise function. So maybe we can use this as a function, or we could also create a noise patterns outside the OpenCL, something like fractal noise, and use that as a source of a fractal, the direction for the vector field to move the pixels. So I'm going to try to use this fractal noise as a source of the noise map because it's more easy to see the result. You could check the vector field directions directly through these textures, so maybe this is more intuitive. Okay, so let me try that way. So since I want to use this as a UV, a direction for X and Y, I'm going to change the signature to UV. Okay, and now I also want to have a negative directions, meaning I want to have a negative to positive value. So what I'm going to do is to make the center to 0, so that you have both negative value and positive value out of this noise. Black indicates that it's a negative value because under 0 it's always black. Okay, for the amplitude I'm gonna make it to 1. So this setup will give you the value in between, I think it's from -1 to 1 as a noise map value. Okay, and this is the map that we have right now. Now this is a bit too noisy, so I'm gonna make it a little bit smoother by making the roughness, lacunarity, and max octative to the minimum, and make it Perlin, and also change the element size to something bigger. Well, it's up to you how you want to set these noise pattern to look like. Okay, so let's say I would like to have something like this. Now this itself doesn't show a vector field as a direction, but it is actually a directional value when you see it as a number. Okay, it's either two float value going to X and Y directions. Now again, if you look at this web page, there is some trick you can copy and paste to show those textures and an arrow, which is pretty cool. I think I saw it somewhere. Yeah, this one. I think this person gives you some snippet to convert a map into a arrow. Yeah, something like that, where you can download, visualize the pixels and as a vector field as one of the component, which is pretty cool. So try it out. I'm not gonna use it, but I'm gonna assume that this is the vector field in some directions. Okay, so if it's yellow, that means it's a bunch. I think it's going to the right top corner because you have red and green mixtured as a positive value. If it's green, I think it's going upward because RGB, so G is Y direction. For the red, I think it's going to the X positive directions. If it's black, then it could be either these or these or these directions. We can't really see that from the color. But anyway, we have those directions from the color. Okay, now what I want to do is to connect this to the OpenCL to use it as a reference. So to do that, we need to have a additional input for this OpenCL. Going into the signature, let's create one more texture called noise. In this case, this is UV, and let's not make it optional. So we have additional source input, which we don't have to write it back to the source, so we're not going to set it as output for this one. Now we also have to bind it inside the kernel, inside the code. So layer, the name is noise, and we don't need any characters before it because it's just an input, and the type is float too. Okay, hopefully, okay, another error here. So noise is missing. Okay, so this is not an optional value, so we have to connect it after we have created. So let's connect this texture and try to use this inside the code. Okay, well, are you guys okay? Hopefully I'm not doing something wrong here. Okay, well, where was I? So now that I have a noise vectors, let's try to replace these movement with these noise as a direction, moving direction. So let's first of all bring up these noise value as a vector value, a float to vector value. So let's call this velocity or something, vel, and just getting the noise as it is. Okay, now I think as the default value of this value is a bit too big, so we have to multiply by some small numbers. So let's say 0.01. Maybe this is still too big, but let's check. Okay, and now now that we have this velocity, we can now update this UV with this velocity and see what happens. Now obviously this is pretty fast, but it does what I want to see. It is transferring the color from one pixel to the other direction. Now let's slow this down a little bit, like 0.05. Alright. Okay, not bad. Now next thing I'd like to do is to now this is just transferring the color from source to destination, just transferring one pixel to the other. What I want to do is to mix the color from the previous one with the current one. So after we have get the previous color, I mean the color from the previous textures, we also want to get the color on the current positions, which is actually the source itself. Okay, so let's call this a previous color. The current color is at source itself. let's update this with prev for now. Oop. Surf with, why did it not serve source? Okay, now what I'm gonna do next is to just add these two colors together and divide it by 2 to have a simple mixture. So for 3, next call is prev call and current call divided by 2 or multiply by 0.5 and use it for the final color. Let's see what happens. Now it looks a bit slower, so let me going a little bit faster here. I just want to check the result. So let's just fix at the end frame and let's see the difference between the next color and prev call and see if there's any changes. Yeah, I do a little bit of changes here. So this is the result of mixturing. This is result of just transferring the color. So now this is interesting, but I also want to make it a bit more dynamic. So what I could do next is to animate the noise value itself. You could also do that. So right now this noise function is fixed at the current positions, but you could animate it by clicking this 3D noise with the animate checked. And then you are now seeing a animated, oops, I think it's just crashed. Wait for it. Okay, there you go. Okay. I think I'm not really following what's written in the comments, but let's open up the crash file. Oop, no file found. Really. Hopefully I have saved. So this is the one that I had here 2 minutes before. Okay, so do we have a mixture? Yep. Alright, so let's go back here, check 3D noise, check if it's animated. Okay. You could also control the speed of this animation by scaling these down. Time scale. Yeah, somewhere around here. And let's see the result. How would that affect the color mixture? Okay, play it. Yeah, getting more interested. Let's increase the time frame. See if it could still work. Maybe it's a little bit fast. I don't know. You could also increase the element size. Getting more interested. Yeah. think I like it. What's good about this is that everything is tiled, so you can actually use it as a tiling image to use it as a textures on any sorts of geometry. Okay, well that's good. Now let's also update the initial color right here. In this case, I really haven't tried yet, but I would like to try to use the function which is explained in here, noise function in OpenCL. So I'm not sure how this works, but let's see if we could use this. So first we need to import the material X noise internal functions, which SideFX seems to prepare for us. Let's create another OpenCL just for backup, or just copy what we have here. Okay. Don't forget to save. Alright. So, can we put it here? Oops, not this one. Not sure where we need to put this. Let's copy this. Vanilla OpenCL does not provide any built-in noise functions, but thanks to Sony Pictures ImageWorks and SideFX team, we have modified version of OpenCL noise library available for import. Yeah, thank you for that. Thank you for that. Can we paste it here? Or maybe not. Yeah. Okay, and let's try to use that. Okay, so we have floor 2, floor 3. I guess we just need floor 2, right? And P is a seed. What does it say? The parameter is, it's a bit hard to see. It's overlaid together. Is this flow 2? Okay, so P is flow 2. Here is, what is it? It's an integer 2. It's periods, I guess. It's a tiling number, I guess. So let's try to use this one. See if it's gonna work. And actually, what I would like to have is not a single float. Or is it? Is it what we want? I want to have a color, so probably I'll use this one as a result of the noise function. I want to get the color as a result, so let's try to use this one. Okay, so we do have UV, which can be used as a seed. Let's just remove the color. Now, float 3 call purling noise and we could stop by using UV as a seed, and for the tiling let's just say 1 and 1. Okay, we got the error because this is not float 4. Okay, so we have to update this to float 4. I'll just call this col4 set. We don't have set. Float 4 call dot x, call dot y, call dot z, and 1. Okay, so did it work? Yeah, it did give me something, which is not really looks like a noise function. Maybe I have to increase this UV value a little bit more. If I multiply it by 10, not so randomish, is it? Maybe I need to also update this periodic numbers. Yeah. Okay. So probably these values and these value will be better set as same value. Yeah, I think. To make it periodic, I guess. So let's have that as a variable. Float. Let's call this peri. And now this one, I need to map it to integer. Okay, so yeah, maybe I could use this as a initial color. Now I'm not sure the range of this one. Is it from 0 to 1 or from minus value to positive value? Does it say anything here? Not sure. Probably it's from 0 to 1. We could make sure that this is within 0 to 1 by using remap node. And this will just clamp the value from 0 to 1, and seems like nothing has changed, so yeah, it was from 0 to 1. Okay, so I guess this is good. I could now replace this with the original UV color and get back to see the result. Yeah, pretty cool. All right. Nice. Nicest thing is that it's tiled. So let's check if it's really tiled by mapping this, using this as a material. Now I saw this technique on this tutorial here, so I'm going to follow the way he used the generated textures as a material. So there is a node called preview material. Preview material, and you can change. You could have a specific geometry to use bunch of textures as a material textures. So what I could do is to place this destination texture to base color, which we're going to paste the texture to the grid. Now let's also change this to perspective view. Now also can change the geometry to something different, like sphere, box, tube, and so on. Let's go with the sphere. Now I also would like to have some like height field to it. So let's get some height field information from this color image. Now this itself doesn't have any height map, so let's see how we could create one. One thing I could think of is to use the the brightness or the contrast of this value of this color as a height map. So let's try to extract the brightness. Now I am not sure if there is any brightness like value we can get from directly using some node. So what I'm going to do is to first of all convert this RGB texture to HSV. In that case, V, which stands for hue, saturations, and value, the value could be used as some kind of a brightness. So we're going to get the V value from HSV and use it as a height field and see what happens. We can now use split, channel split, and get the blue one, which must be the value for the HSV color, and connect it to height. Okay, now it's a bit offsetting a bit too much, but I do see some effect here. Let's increase the divisions for more smoothness, and let's also reduce the maximum height going into the normals and displacement somewhere around here. Like that. Cool. We could also have some smoothness to the height if you use something like blur. You kind of smoothen the edge if you want. Like that. So something like that. And what's great about this is that even though it seems to have so many details, you still can animate in real time in preview, which is pretty cool. Pretty cool, and everything is tiled, so no, it's pretty smooth everywhere. You could also change the number of tiling, going back to the UV scale. Yeah, that's like that. Okay. So, looks pretty good. Pretty good. And that's what I wanted to show for today. Which was pretty simple setup. I mean, it's all the steps that is borrowed from all the places that I learned, from here, from here, from here, from here, and the sample code of the OpenCL solver. But I thought it will be good to share what I found out, so maybe some people might found it helpful, useful in some case. So hopefully you found something new here. Okay, so that's what I wanted to show it for today. I think I'm gonna end this with adding some render to this one. Just like the guy here told us, you can directly use these Copernicus textures in a loop network. You can scene import. You can have so this is only, I think this only works on Windows where you have GPU, I think. And I'm going to create a Calma sky dome light. Okay. Looks pretty dark. Where did I? think I'm missing something here. Calma, dome, skylight. Yeah, no, physical sky, sorry. Increase the intensity a little bit. Let's also use the camera. And we could just try to render this using Calma. I mean, but before doing it, I might want to do something else, but let's see if I could render it. Oop. Okay, something weird has happened. I think need to recreate the material for the Calma. So let's do that. Okay, I'm going to create an assign material here. And instead of using scene import all, which is, I guess it's fine. Let's name this scene. I'm going to create an assign material. Let's try to I think I also need to create the material itself. So let's let me see where I could do that. I think I needed to use edit material properties beforehand. Now these part I am not really don't really know much about stuff, so please bear with it. Now I think it's not it. Create what did I need it to do here? Forgot. Let me see. Let me check. So I think I was creating a quick material somehow. I forgot. Quick shader. Quick shader. Is it? Quick surface material. Is this it? Maybe this is it. Okay. Sorry for the hustles. I am not really good at rendering, as you can see. Okay, now we need to import the textures, and I also need to assign the material to the geometry. The geometry that I want to assign is the scene that I have imported. So can I just say like this? And the material is Okay, I don't think it's working. Let me... Probably I need to say Geo1. Nope. Nope. Okay, let me check the comment. You can get tasks quickly by dragging them over the geo spreadsheet. Okay. You can switch them build slowest. View, drag and drop the geo source. Important to know, like diffuse into the shader with OP. Okay, I'll do that. I will do that. First of all, I think the material is not assigned to the geometry yet. So let's see how I can fix that. So this is importing the object. Okay, so this is... I don't really need to import the material because I'm creating one here. And this... In map parameter cup node path. I think I'm missing something here. Scene mesh 0. Okay. Let's try. Sorry for all the hassles. Okay, let's see if I can use a apostrophe. Nope. How's this? Nope. Or can I just say like that? Okay, maybe this is working because I see some updates on the specular. Okay. Well, sorry for all that. Okay. Let me practice these. Okay, now I am going to connect these textures that I want to export to null. Let's call this cul. And the other one, height. Okay. And I heard that if you copy this node, you can actually copy the path to it. So going back to the stage, to material property, where you have color map. Let's paste it. Okay, now, okay, someone has mentioned I need to have an OP. Okay, finally. Okay, next we have bump, height map. Did I name it height? Okay, let me see if it's gonna change the... Oop. Yep. Okay. Okay, yeah, so it seems to work. Alright, then finally trying out the rendering. Okay, well, I'm still learning these renderings, but very really beginner to these rendering stuff, but really thank you for all the informations. It's really helpful. Maybe you can do OpenCL for algorithmic design series one day. Well, hopefully I can if I'm fluent on OpenCL on someday. That'll be cool. Okay, now done. This is the end of the live. Well, I'm not sure how you felt about the stuff, but maybe it was too basics for most of you guys, but I hope you liked it. At least I learned a lot through all the stuff that I went through using OpenCL for feedback loop, and which was pretty interesting. I found it really, I mean, I think it could be really powerful for many cases. I also want to try using OpenCL for other purposes, like importing the subgeometry directly to COPS and Copernicus and update the textures based on it. And probably you could also combine it with a subsolver. That could also be pretty fun. So yeah, that all sorts of things that I would like to try with these great new features from Houdini 20.5. So thanks for side effects, and thank you all for joining the live. And I think I have just crashed it again. No. Did I saved it? I don't know. Yeah, it happens a lot. Okay, the last time I saved is like 3 minutes ago. Not bad. I'll check the state of the current file and I'll finish the live stream. Thank you very much for joining, and thank you all for all the comments. Gonna get back. I'm gonna look back to all the comments later, because some of the comments I couldn't follow. Do we have a crash file? How come I don't have a crash file? Okay, so not bad. I think I had it till the end. Okay, height field is not updating. I think it's due to... yeah, it's fine. Okay, so that's it. Thank you very much for joining. I will going to upload the files that I've created, which hopefully is helpful for some of you. And you can download the file from the link in the description page of this YouTube live stream, as always. And yeah, that's it. Try to do something else next week as well. Maybe another OpenCL or maybe Vex, not sure yet, but something I found interesting for sure. Okay, so that's it. Thank you very much, and good night. It's midnight, almost midnight on Sunday, on Japan time. It's time for us to go to sleep. Time for me to go to sleep. Okay, Bye. Ciao, ciao.